Welcome to Aurelius Explainer. Tonight, settle in. There is no hurry here, and nothing you need to do but breathe and let the sound of these words carry you somewhere very far down, somewhere very old and very quiet, somewhere most people will never go. Make yourself comfortable. Let your shoulders drop. Let the day, with all its small, unfinished things, begin to loosen its grip on you, because where we are going, none of it can follow. We are going to the bottom of the sea, and down there, 1,000 meters below the surface of the Gulf of Mexico, in a darkness so complete that no light from the sun has ever touched it, there is a lake. At the bottom of the ocean. Take a moment with that slowly, the way you would turn an unfamiliar object over in your hands. A lake is something we know. A lake has a shore. A lake has a surface you can see, a surface that catches the light, a surface that ripples when you trail your fingers across it. A lake is a thing that sits inside the land, held in a hollow, with the world standing dry around it. That is what a lake is. That is what a lake has always been. And yet down there in the deep dark, 1,000 meters under the waves, there is a body of water that does all of those things. It has a shoreline, it has a surface, a clear and definite surface, with the rest of the ocean above it like air above a pond. It has gentle waves that move across it when something disturbs them. And it sits, this lake, in its hollow on the seafloor, perfectly still and perfectly separate. A pool of water resting inside the water, as though the ocean had somehow grown a skin, and beneath that skin had cupped a smaller, stranger sea of its own. A lake at the bottom of a lake. A pond inside the ocean. It should not be there. By everything we feel we know about how water behaves, it simply should not exist, but it does. It has been seen. It has been filmed in the cold beam of a submersible's lights by people sitting in metal spheres 1,000 meters down, watching with their own eyes as the robotic arm of their vehicle reached out and dipped into that lower surface and made it ripple exactly as a pond ripples when a stone breaks it. The waterline wobbled and reformed. Little waves spread out and faded, and the people inside who study the deep ocean for a living, who have seen things that would keep most of us awake for the rest of our lives, sat there in the dark and could hardly believe what they were looking at. That is the feeling I want to give you tonight. Not fear, not a jolt, just that slow, widening sense of wonder, the kind that does not race your heart, but loosens something behind your ribs, the feeling of the world being larger and stranger and gentler than you had been told. We are going to wander, slowly and without urgency, into the strangest waters on Earth. Underwater lakes, underwater rivers, with banks and meanders, and what people have called rapids. Shimmering glass surfaces that you can see while you yourself are deep underwater. Pools that kill almost everything that touches them, and yet are crowded at the edges with life. And we are going to take all of it apart gently until the impossible becomes not less wonderful, but more. Because the truth of how it works turns out to be stranger and more satisfying than any story we could have made up. But before we go any further down, let me ask you something quietly. Where in the world are you listening from tonight? I always find myself wondering. Somewhere out there, a window is dark, a lamp is low, a city is sleeping, or a countryside is silent. And you are lying there, letting this voice walk you down into the deep. If you feel like it, leave a note in the comments and tell me where you are. I read them. It is a strange and lovely thing to think of all of us drifting off inside the same buried, half-lit world, scattered across the real one above. And if you are new here, and you would like more of these slow journeys into the quiet and the unexplained, You might gently subscribe, so the next one finds you when you need it. There. That is the only thing I will ask of you all night. Now let us go back down. Because here is the question that Lake leaves hanging in the dark, the question that makes your mind reach for the word impossible. How? How can there be water that pools beneath water? Water is water. Pour a cup of water into a bathtub, and it does not sit there in a neat little lake at the bottom, holding its shape, refusing to join the rest. It mixes, it vanishes into the whole. That is what water does. So how, in the cold and the dark at the bottom of the Gulf of Mexico, does one body of water lie down inside another and stay there, separate, with a surface you can ripple? And the answer we will come back to again and again tonight, the answer I want you to carry down into sleep like a warm stone in your pocket, is this. It isn't magic. Salt makes water heavier, and heavier water sinks and gathers and settles into the low places, even when those low places are already full of water. That is the whole secret. Hold on to it. We will turn it over from a dozen different angles before the night is through, and every strange thing we meet down there, every lake, every river, every shimmering pane of glass beneath the sea, will dissolve back into that one gentle, ordinary rule. Heavier water sinks, the same reason oil floats on top of a puddle, only turned upside down. The same reason cold air slides down into a valley on a still night and pools there in the low ground while the warmer air rests above it. The same reason, really, that a stone sinks and a cork floats. Things that are denser go down. Things that are lighter stay up. The ocean obeys this just as faithfully as your kitchen does, and when you make a body of water heavy enough, the rest of the sea will float on top of it like air floats on a pond. But we are getting ahead of ourselves, and there is no need to hurry. We have all night. Let us go back to that lake, and to one lake in particular, because it has a name, and the name alone tells you something about the place we have come to. They call it the Jacuzzi of Despair. It was described properly, studied and written up in 2016 by a team of researchers led by Erik, a deep-sea biologist at Temple University, a man who has spent a great deal of his life looking at the parts of the ocean the rest of us will never see. And what they found, sitting down there in the Gulf of Mexico at a depth of around 1,000 meters, that is roughly 3,300 feet, more than half a mile of black water stacked above it, was a small, round, almost perfect pool. Picture it, slowly. It is circular, more or less, a rough ring on the floor of the abyss. Around its edge runs a raised rim, a low wall of rock and mineral, so that the pool sits inside it like water inside the lip of a basin. Across, it measures something like 30 meters around its circumference. Close enough, if you are lying in bed trying to see it, to picture a generous garden pond or a small backyard pool, the kind you could walk around in a leisurely half-minute. And at its deepest point, it goes down about 3.5 meters, somewhere near 12 feet, deep enough that a tall person standing on the bottom would be well over their head. A small pool, a picturable pool, a pool you could imagine sitting beside. And it shimmers. Under the lights of the submersible, the surface of the Jacuzzi of Despair has a mirror-like quality, a faint, oily sheen, smooth and still and reflective, so that it really does look for all the world like a hot tub left running in some impossible place in the cold and the dark where no hot tub has any right to be. There is the surface, there is the shore, there at the rim you could very nearly lean over and look at your own face in it. And that is the trap. Because everything about it invites you in. It looks warm, and it is warm. The brine inside it carries heat up from deeper, warmer sources within the seafloor, so the pool sits there several degrees warmer than the freezing ocean all around it. a little pocket of inviting heat in a world of cold. It looks calm, it looks like rest. After the long descent through the lightless miles, here at last is something that resembles a pond on a summer evening, still and warm and waiting. But it is one of the most lethal patches of water on the face of the earth. The pool is brine. Water so heavy with dissolved salt that, as we said, it cannot mix with the sea above it. But it is not only salt. Dissolved into that warm, still water is a great load of methane and a great load of hydrogen sulfide, the gas that gives rotten eggs their smell, a substance that to most living things is simply a poison. And there is almost no oxygen in it at all. None of the dissolved oxygen that nearly every animal on this planet needs in order to draw a breath, in order to keep its body running, in order to live. The Jacuzzi of Despair is warm and beautiful and effectively without air. It is a basin of poison wearing the face of a hot tub. So consider gently what happens to the creatures of the deep who do not understand any of this. A crab, picking its slow way across the sea floor in the eternal dark, doing what crabs do, scavenging, wandering, feeling its way along. A small amphipod, an isopod, one of those many-legged scuttling things that make their living down there in the cold. They cross the raised rim, they tumble in, or they wander in, drawn perhaps by the warmth, or simply blundering across the edge in the blackness. And in that heavy, airless, poisoned water, they cannot breathe, and they die. But here is the strange and quiet part, the part that turns this from a horror into something closer to a still life. They do not rot. The same chemistry that kills them also preserves them. The brine is so salty, so airless, so hostile to the bacteria of decay that the bodies do not break down the way a body breaks down in the ordinary sea. They are pickled, held, suspended in that warm, clear water like specimens in a jar, like fruit preserved in syrup, perfect and unmoving. The researchers found them lying within the pool and ringed around its edges, crabs and amphipods and small creatures, dead and yet whole, arranged on the bottom and along the rim in their dozens, a gallery of the lost. A bathtub ring of the perfectly preserved dead, recording, body by body, the long and patient lethality of the place. Every one of them a small creature that crossed a line it could not see, into water that looked like rest and was instead an ending. It is a sobering image, and I tell it to you gently, with no sharpness, because there is no cruelty in it, only the indifferent chemistry of the deep. The pool does not mean any harm. It is only being what it is. Heavy water gathered in a hollow, holding its breathless stillness for who knows how many thousands of years. And that is where the name comes from. The Jacuzzi of Despair. A hot tub of despair, the researchers called it. The warmth and the shimmer promise comfort. The chemistry delivers death. The two things sit together in that one small round pool, the invitation and the trap, the warmth and the poison, and you cannot have one without the other. But now hold that image of death and let me give you the other half, because the deep does almost nothing in a simple way, and the Jacuzzi of Despair is, at one and the same time, a death trap and a life ring. Because while the inside of the pool is a place where almost nothing can live, the rim of the pool, that raised wall of rock around the lethal water, is crowded with life. Crowded. Dense beds of mussels grow along the edge, packed shell against shell, a whole living border around the deadly pool. And around and among them tube worms and shrimp and crabs, the very same kinds of crabs that fall in and die. They live right there at the very lip of the thing that kills, thriving in a ring around the water of death. How? How can the edge teem with life while the center is a graveyard? It comes back once again to that load of methane and hydrogen sulfide, the very poisons in the pool. Because to the right kind of creature, those are not poisons at all. They are food, they are fuel. We will come to the full strangeness of that later, slowly, when we talk about how life can be built without a single ray of sunlight, on chemistry alone. For now, simply hold the picture because it is one of the most quietly astonishing things in all the ocean. A pool that kills what falls in. A rim that blooms with life on the very chemicals that do the killing. Death in the middle and a garland of life around the edge. The two of them inseparable, each one the reason for the other. A death trap and a life ring at once. That is the Jacuzzi of Despair. Now I want to take you back to that surface, the surface of the pool, because it is the detail that I think troubles the mind the most, the one that keeps tugging at that word, impossible. And I want to let you rest in it for a while before we go any deeper. When the submersible came down to the Jacuzzi of Despair, and when other vehicles have come down to the other brine pools scattered across the floor of the Gulf, the pilots and the scientists watch something that genuinely unsettles the ordinary sense of how the world works. They watched the robotic arm of the vehicle reach out toward the pool. And as it touched the surface of that lower water, the surface behaved exactly the way the surface of a pond behaves. It dimpled, it rippled, little waves ran out from the point of contact and spread across the pool and lapped against the far shore and came quietly back. The instruments, dipping in, broke the surface and left a wake, the way a paddle leaves a wake. The whole pool sloshed gently and then settled, and the interface reformed itself, smooth and reflective once more, as though nothing had happened. And the people watching could see the line. That is the part that astonishes. There is a line, a clear, definite, visible boundary between the ordinary seawater and the heavy brine below it, sharp enough that you can point to it and say, there, that is the surface of the lake, the way you would point to the surface of a pond from the bank. Above the line, ordinary ocean. Below the line, the dense and deadly brine. And the line itself is a real physical thing, a surface you can ripple and disturb and watch settle. It is the strangest sort of shoreline in the world. The water above is not air, but it might as well be for all the brine cares. To the brine, the entire ocean above it is the sky. The interface is its surface, the place where its little waves break, the lid of its small, dark world. And around the edges, where the pool meets the higher floor of the seabed, there is a shore, an actual margin where the lake ends and the open seafloor begins, often ringed with bright mats of bacteria, white and yellow and orange, marking the boundary like a tide line marks the edge of the sea. I want you to lie there and really see it. The submersible hangs in the black water, its lights pooling on the scene. Below it, a small round lake, its surface mirror still, faintly shimmering, faintly oily under the lamps. A pale rim around it, beds of mussels crowding that rim, alive. And here and there within the clear water, the preserved shapes of the things that fell in, held motionless in the warm and poisoned stillness. No wind, no sound, no light but the one we brought. A pond at the bottom of the sea, 1,000 meters down, going about its silent business in the dark exactly as it has done for thousands upon thousands of years, with no one to see it, no one to know it was there. Until a handful of human beings descended in a metal sphere and put a light on it and could hardly believe their eyes. That is where we begin tonight, with the impossible thing fully and clearly seen. A lake with a shoreline and gentle waves, warm and lethal and crowded with life around its rim, resting in a hollow on the floor of the Gulf of Mexico, half a mile beneath the waves. And I have told you already the seed of how it is done. It isn't magic. Salt makes water heavier. and heavier water sinks and gathers and settles into the low places, even when those low places are already full of water. You can feel, perhaps even now, how that ought to be enough to explain it, how something in that simple sentence already begins to dissolve the impossibility, the way warmth dissolves a knot of tension you have been carrying without noticing. But there is so much more to it, so many gentle layers still to unfold, and that is what the rest of our night together is for. Because once you truly understand why the brine pool sits there and will not mix, you understand a great deal more than one strange pool in the Gulf. You begin to understand a river. Yes, a river. A real one, with banks and bends and the kind of features people have called rapids, that flows beneath the surface of the Black Sea, carrying as much water every second as one of the largest rivers on the face of the earth, and going about it all in the dark beneath the waves, where no one for almost the whole of human history ever suspected a river could be. You begin to understand the shimmering panes of glass that divers swim through in the flooded caves of the Yucatan, surfaces of water you can see while you are deep underwater, blurring and bending the light like a sheet of moving glass. You begin to understand pools in the Red Sea, hot enough and rich enough in metals that there is gold and silver dissolved in the water, and basins in the Mediterranean, so salty and so airless that the only things living their whole lives in them are creatures that have learned to do without oxygen entirely, the first animals ever found that live from birth to death with no air at all. You begin to understand the slow tube worms ringing these dark pools, some of them alive for more than 250 years, possibly more than 300, in a place the sun has never once reached. And you begin to understand the ice that burns, methane locked inside cages of frozen water resting on the seafloor, dirty-looking and quiet, that will fizz and dissolve and catch fire if you ever bring it up into the light. All of that is waiting for us down there in the dark, and we will come to all of it slowly, with no rush at all, each strange thing in its turn, each one set down gently and then taken apart until the wonder turns into understanding, and the understanding turns, somehow, into a deeper kind of wonder still. But for now, let us simply stay a little longer beside that first impossible pool, and let the question settle over you the way the brine settles into its hollow, heavy and calm and unhurried. A lake with a shoreline 1,000 meters down, warm and lethal and crowded with life around its rim. A surface you can ripple, a shore you can stand upon, waves that lap and fade, bodies held perfect and unmoving in the clear, warm poison, and around it all the eternal black water of the deep, pressing in on every side, and the line, that sharp and astonishing line, holding firm between the ocean and the lake, between the water and the water, refusing to blur, refusing to mix, holding its small, dark sea apart from the great one above it. How can that line hold? What keeps the two waters from becoming one? Why does the lower water lie down and stay, instead of rising up and joining the rest, the way the water from your cup joins the bath? The answer is heaviness. The answer is salt. The answer is the same gentle rule that lets oil rest on a puddle and cold air pool in a valley and a stone go down while a cork stays up. And in a little while, when you are warmer and heavier yourself, sinking down into your own quiet hollow, we will follow that rule all the way to the bottom and see exactly how the sea performs its impossible trick. We will measure how much salt it takes. We will find out where in all the world the sea could possibly have gotten so much salt to pour into one small pool. We will go back 200 million years to a time when the Gulf of Mexico was not an ocean at all, but a shallow, baking sea that filled and dried and filled and dried again, laying down floor upon floor of salt that is still down there now, buried and patient, bleeding its brine slowly upward into the dark. But that is for the next stretch of our journey, and there is no need to reach for it yet. For now, just rest here at the edge of the first impossible lake and let the wonder of it hold you the way the brine holds its silent stillness. The deep is not in a hurry. The pool has been there for thousands of years, and it will be there for thousands more, mirror still, warm and lethal, and ringed with quiet life, keeping its strange surface smooth in the dark. Let your breathing slow to match it. Let the line between waking and sleeping grow as soft and as gentle as that shimmering surface 1,000 meters down. There is nothing you need to solve tonight. There is nothing you need to hold. The mystery will keep. The pool will keep. The whole strange, layered, sunken world will keep, waiting in the dark while we go down into it together, slowly, one quiet marvel at a time. Picture the boat first, before the pool. A small research vessel on the surface of the Gulf somewhere off the coast, the water above it ordinary and blue and busy with the things ordinary water does. And below that boat, straight down through 1,000 meters of dark, an arm reaches out from a submersible no bigger than a small car, and a camera turns, and there in its light is something that should not be possible. A surface, a real surface, smooth and reflective, with a faint sheen to it like oil on a puddle, holding the light back the way only the top of a liquid can. And the camera tips lower, and there is a shore. An actual shoreline, a rim where the lake ends and the seafloor begins, ringed with a pale crowding of mussels packed shell to shell. And beyond that rim, the dark plain of the bottom stretching away. This is the thing the scientists could barely believe when they first saw it. You can watch the footage of these dives and you can almost feel the people behind the cameras going quiet. There is a lake down here, not a pool of water that looks a little different. A lake with everything a lake on land would have. A shore you could walk along if you could walk down there. A surface a fly might land on if there were flies 1,000 meters under the sea. And when the submersible's arm dips into it, the surface ripples. It actually ripples, little rings spreading out across the top of the pool, exactly the way they spread when you trail a finger across a still pond at dusk. And then they settle, and the surface goes smooth and mirror flat again, as if nothing had touched it at all. Tell me, before we go any deeper, where in the world you are listening from tonight. I always like to imagine where you all are, scattered across the dark side of the planet, some of you near the sea, and some of you 1,000 miles from any coast, all of us drifting towards sleep together. Leave it in the comments if you feel like it, and if these slow journeys into the strange places of the world help you find your way to rest, you might think about subscribing so there will always be another one waiting whenever you need it. There. That is the only thing I will ask of you. The rest of this hour is just for sinking into. So, a lake at the bottom of the sea with a shoreline and a surface and little ripples that fade. It looks like a violation of everything water is supposed to do. And yet, remember the rule, the quiet rule, we are going to follow all the way down. It isn't magic. Salt makes water heavier. That is the whole secret, and we will keep coming back to it like a hand on your shoulder every time the sea does something that seems impossible. The water in that pool is so crowded with dissolved salt that it has become heavier than the ordinary seawater above it, and heavier water does not rise and does not mix. It sinks, it settles into the lowest hollow it can find on the seafloor, and it stays there, a separate liquid lying on the floor of the ocean like rainwater pooled in the bottom of a boat. That is all a brine pool is. A puddle of water too heavy to float away. There is one of these pools in particular I want to bring you to first because the people who found it gave it a name that tells you almost everything you need to know. They called it the Jacuzzi of Despair. It sits about 1,000 meters down in the Gulf of Mexico, 3,300 feet beneath the waves, and it was described in a study back in 2016 by a team that included a researcher named Erik of Temple University. It is roughly circular, only about 30 meters around, and at its deepest perhaps 3.5 meters, 12 feet, with a raised rim around it like the lip of a bath. And here is the first surprise hiding inside the surprise. It is warm. The brine carries heat up from deeper, warmer places below, so the pool sits there at the bottom of the cold, dark sea, actually warmer than the water around it, gently steaming in a manner of speaking, like a hot tub left running in an empty house. A jacuzzi sunk 1,000 meters into the floor of the Gulf. And then the despair. Because that warm, inviting pool is a killing thing. The brine is not just salty, it is laced with dissolved methane and hydrogen sulfide, and it holds almost no oxygen at all. Anything that wanders in does not come out. Crabs, amphipods, little isopods. Whatever falls or strays over that mirror-flat rim dies, and the toxic, oxygen-starved brine does not let them rot. It keeps them. It pickles them. The researchers found carcasses lying inside and around the pool, perfectly preserved, a kind of bathtub ring of the dead, recording everything the pool has ever caught. A hot tub that looks like an invitation and is, in fact, a trap, holding its victims in clear, warm, lethal stillness on the floor of the sea. And yet, crowding right up to the deadly edge of it, ringing that lethal rim shell against shell, are the mussels. Thriving, alive. A wall of living things gathered around a pool that kills. Hold that strange double picture in your mind as you drift, a death and a garden sharing one shoreline. And we will come to understand it soon enough, slowly, with nothing to fear, the way we understand everything down here in the dark. And so the question the pool insists on, the one that will not let you rest without an answer, is simply this: how? How does water pool beneath water? How does a liquid gather itself into a lake inside another liquid, hold its own surface, wear its own shoreline, keep its own warmth, and refuse to dissolve upward into the ocean pressing down on it from above? It seems to ask for magic, or for some invisible wall, some membrane we cannot see. There is no wall, there is no membrane. There is only weight. This is, when you follow it to its root, one of the oldest and most ordinary rules in the physical world. Oil sits on water because oil is lighter than water. Cold air settles into a valley on a still night because cold air is heavier than warm air, and it drains downhill the way a slow river drains, pooling in the low places, lying there in the pre-dawn quiet, while the warmer air floats overhead. You have felt this if you have ever walked through a meadow before sunrise and stepped into a pocket of cold that was not there a moment ago, a cold that gathered in the dip of the ground and stayed, held by its own density, bounded above by warmer air that will not mix with it until the sun rises and stirs everything together. The valley of cold air is a lake that happens to be made of air. The brine pool is a lake that happens to be made of extremely salty water. The principle is identical. The only difference is scale and darkness. Ordinary seawater, the water of open oceans, the water that fills the Gulf of Mexico for hundreds of miles above the pool, holds about 35 parts of dissolved salt for every 1,000 parts of water. 35 parts per 1,000. That is the baseline, the number that oceanographers use as a kind of normal, the salinity the ocean has maintained across long stretches of its history. 35 parts per 1,000 is already enough salt to sting your eyes, enough to make a hard-boiled egg float higher in the glass, enough to make a swimmer feel slightly lifted, but it is nothing compared to what sits in the pool below. The brine in a pool like the Jacuzzi of Despair reaches concentrations 3 to 8 times that ordinary number, not 35 parts per 1,000, but 120, or 160, or 200 parts per 1,000. Think of it this way. Imagine you have a glass of ordinary seawater, which is already noticeably salty to the tongue. Now imagine dissolving into that same glass 3 times the amount of salt you already put in, and then perhaps another half portion on top of that, stirring it until it holds everything it can hold, until it is thick with dissolved mineral in a way that ordinary water simply is not. That is approximately what fills the pool, and water that holds that much dissolved salt weighs more. It is measurably, substantially, physically heavier than the water above it. Not because of any mystery, but because you have added mass. The water has absorbed the mass of salt into itself, and it is heavier for it, the way a wet sponge is heavier than a dry one, the way a bag of wet sand is heavier than the same bag of dry, and heavier fluid sinks, lighter fluid floats above it. These are not metaphors, they are the arithmetic of gravity working on mass, and they produce a boundary so stable, so resistant to disturbance, that the 2 layers simply do not mix in any practical human time frame. The brine settles into the low places of the seafloor and stays. The ordinary seawater floats above it and stays. Between them, where the salinity shifts from the extreme to the ordinary, there is a zone of transition so sharp that it can be only centimeters thick, and that zone is where things get beautiful and strange. Scientists call this kind of boundary a pycnocline. Pycno from the Greek for dense or thick, cline from the Greek for slope or gradient. A pycnocline is any layer in the water column where density changes steeply with depth, and the word covers a family of related phenomena depending on what is causing the density change. When the change is driven by salinity, the way it is in a brine pool, the specific name is a halocline. Halo from the Greek for salt. When the change is driven by temperature because cold water is denser than warm water and sinks beneath it, the name is a thermocline. In practice, the real ocean layers its water by both salinity and temperature at once, and the combined density boundary gets the general name pycnocline. But whatever you call it, the effect is the same. A density boundary in water is one of the most stable structures in nature. It resists mixing the way a bar of metal resists bending. Not because it is hard, because it is simply the lowest energy arrangement. The heavy is below and the light is above, exactly where gravity wants them, and disturbing that takes more energy than the ocean usually provides. You can see this boundary. That is the part that startles people who first encounter it. You would expect invisible chemistry to be, well, invisible, but the halocline at a brine pool or at a cenote, one of the limestone sinkholes of the Yucatan Peninsula in Mexico, where fresh rainwater overlies intruding seawater, shimmers, it blurs. It looks like glass that has been breathed on, or like the surface of hot air rising from summer asphalt, a rippling, transparent layer that bends the light passing through it. The reason is refraction. Light bends as it passes from one medium to another, and it bends differently depending on how dense the medium is. When you look from above through the ordinary water and into the sharp transition zone where salinity is changing rapidly over a very short distance, the light coming up from below bends differently than the light above, and the boundary catches that difference and scatters it back as shimmering, a visual distortion that says, there is something here, a threshold, a surface within the surface. Divers in Yucatan's cenotes have filmed this for years, and the footage is startling every time. You are underwater, you are submerged, you are surrounded by water on all sides, and yet there, a meter or two below you, is what looks unmistakably like the surface of a pond, rippling, reflective, catching the light, a mirror buried inside the water. You reach through it and your hand seems to enter another world. At the brine pools of the Gulf of Mexico, the effect is similar, and the submersible cameras capture it with the same quality of strange wonder. The arm of a remotely operated vehicle dips below that rim, below the surface of the brine, and the instrument enters the dense liquid below with the small, clear, unmistakable resistance of entering a pond. ripples spread from the disturbance. The surface reforms. And the researchers, watching from their screens hundreds or thousands of meters above, sitting in their ship in warm air, find themselves watching what looks exactly like footage of a lake surface disturbed by a stone. Because it is a lake surface disturbed, in this case by a robot arm, and the lake happens to be at the bottom of the sea. The question of where the salt came from is its own slow story, and it is a very old one. The Gulf of Mexico was not always the deep water body it is today. Roughly 170 to 200 million years ago, in the Jurassic period, the Gulf was a different kind of place altogether, younger, shallower, a basin that opened and closed and in certain phases became something closer to an inland sea, periodically isolated, repeatedly exposed to the heat of the sun, and repeatedly allowed to evaporate. When seawater evaporates in a contained basin, the water goes and the salt stays. It cannot evaporate. It has nowhere to go, so it accumulates layer by layer as the water comes and goes, building deposits of mineral that harden over geological time into rock, salt rock, which is what evaporate means. Rock that is the chemical residue of an evaporated sea. The layer that geologists call the Louann Salt is the deep, thick result of that process. It is a formation of salt and associated evaporate minerals buried far beneath the floor of the northern Gulf of Mexico, running under the sediment that has been deposited above it over the 170 or so million years since it formed, layer by layer, as the Gulf deepened and filled and the sediment of eroding continents rained down. The Louann Salt is, in a sense, the chemical memory of a sea that no longer exists. It is the ghost of Jurassic evaporation, pressed flat and buried under an ocean. But salt is not passive once buried. Salt behaves in ways that solid rock does not, because it is relatively soft and, more importantly, because it is less dense than the sediment piled above it. And here the same density logic returns, only in reverse. The overlying sediment is heavier than the salt beneath it, and in geological time frames, under the enormous pressure of kilometers of accumulated rock and water, the denser sediment pushes down on the less dense salt. The salt, unable to compress further, flows. Not quickly, not in any way a human lifetime would notice, but in the million-year timescales of geology, it flows the way a slow and almost infinitely viscous liquid flows, squeezing upward through weaknesses in the sediment above it, rising in columns and domes and ridges and sheets, pushed by the weight of the world pressing down from above. This is what geologists call salt tectonics, and the Gulf of Mexico's seafloor is one of its most dramatic expressions on Earth. The salt domes and ridges that salt tectonics creates push up through the sediment and distort the seafloor into a landscape of mounds and basins, rises and hollows, a rugged and architecturally complex terrain that from the surface of the ocean gives no hint of its existence. In the low places between these salt-driven rises, the seafloor forms what are called mini-basins, small enclosed depressions that are the direct product of the underlying salt movement. And into these depressions, fluid flows, the circulating water of the deep sediment moving along very slow underground paths shaped by pressure and permeability, encounters the salt formations and dissolves them. It takes the salt up into solution, becomes brine, and follows the pressure gradients toward lower pressure, which means it rises, working upward along faults and cracks until it reaches the seafloor and seeps out. The mini-basin provides the bowl. The dissolving evaporite provides the chemical load. Gravity provides the rest. The brine flows to the lowest point and pools, and in the low depression of a Gulf of Mexico mini-basin, it rests and accumulates and deepens over time until there is a lake, a dark and lethal lake, a kilometer down, 3 kilometers down, however deep the depression happens to sit. This process is not fast by human measure, but it is old and continuous. The Louann Salt has been supplying brine to the Gulf seafloor for an immense stretch of time, and the pools that form above it are the product of a slow, patient chemistry measured in thousands and perhaps millions of years. They are not accidents. They are the inevitable result of where this particular chemistry meets this particular geography, which is why the Gulf of Mexico has not one brine pool but many scattered across the seafloor in the mini-basins that salt tectonics has carved. There is another quality of these pools that the simple density explanation does not immediately suggest, but that the Jurassic salt source helps account for: the warmth. The Jacuzzi of Despair earns the jacuzzi in its name not only from its shape, but from its temperature. The brine inside the pool is warmer than the surrounding deep seawater, which at those depths, 1,000 meters below the surface, is very cold indeed, close to 2 degrees Celsius, nearly freezing, the kind of cold that has no relationship to any cold you meet in ordinary daily life. The brine is not hot, it is not dramatically warm, but it is measurably warmer than the water around it because it carries heat from deeper sources. The fluid that dissolves the salt and rises toward the seafloor passes through warmer layers on its way up, through the geothermal gradient that makes the Earth's interior warmer as you descend, and it carries some of that warmth with it. The pool it forms sits slightly warmer than its surroundings, a small and specific thermal anomaly on the floor of the cold, deep sea, which is, under the lights of a submersible, another feature that looks almost designed. A warm pool at the bottom of the cold ocean, still and circular and inviting, the way something inviting in a story is always slightly too perfect, always hiding what it costs. The cost is recorded on the rims and in the shallows of the pool. What researchers have found there, and what you can see in the footage if you look carefully around the bright rim of mussels, is a record of the pool's history written in the bodies of what it has taken. A bathtub ring. Not a ring of soap scum and mineral deposits, though there are mineral deposits too, but a ring of preserved dead things, crabs and small crustaceans and whatever else wandered too close or toppled over the rim, lying in the brine or scattered at its edges, not decayed, barely changed, because the brine that killed them also keeps them. Oxygen is what drives decay. The microbes that break down organic matter, the bacteria of decomposition, need oxygen to do their work. In the brine pool, where the oxygen content is effectively zero, they cannot work. The body lies, the brine holds it, and over time, over the slow accumulation of the pool's history, the edges collect this record, an archive of every casualty, a perfectly preserved ledger of what the pool costs. There is something both melancholy and, in its way, honest about that ring. It does not hide what it is. The pool does not disguise its lethality. It presents it openly in the bodies it keeps, the same way a carnivorous plant keeps its dissolved insects visible in its cup, not concealing the mechanism but displaying it, and then immediately adjacent to that display, alive and dense, and crowding the chemical boundary at the rim, the mussels, alive where the pool's chemistry is extreme enough to be useful, but not so extreme as to be lethal, living in the gradient, thriving in the transition zone that would overwhelm anything venturing a little farther in. The boundary of a brine pool, that narrow zone where the extreme chemistry meets the ordinary deep sea, is one of the most productive places in the deep ocean. Not productive in the way a coral reef is productive, not flooded with light and color, but productive in the chemical sense, rich in the specific molecules that certain forms of life have learned, over evolutionary time, to use as fuel. Methane rises from the sediment here. Hydrogen sulfide seeps upward where the chemistry allows, and those molecules to the life that rings the pool are food, or more precisely, they are the raw material for a form of energy metabolism that has nothing to do with the sun. Most life on Earth is solar. The chain of energy nearly always begins with photosynthesis, with a plant or an alga or a cyanobacterium capturing sunlight and using it to build organic molecules, and every animal that eats a plant and every predator that eats that animal is spending energy that began as sunlight hitting a leaf or a cell membrane somewhere closer to the surface of things. 1,000 meters below the surface of the Gulf of Mexico, sunlight does not reach. It is not merely dim down here, it is absent. Absolute darkness except for the occasional blue-white glow of bioluminescence and the lights of the rare submersible passing through. Nothing down here has seen sunlight, and nothing ever will, because the ocean is opaque to light beyond the first few hundred meters. The solar chain has no purchase here, and yet things grow and eat and reproduce, and have been doing so for a very long time, tethered not to the sun but to the chemistry seeping out of the seafloor. The process is chemosynthesis, and it is the energetic foundation of every community that rings a brine pool or clusters at a cold seep. Where photosynthesis uses sunlight to power the conversion of carbon dioxide and water into sugars and oxygen, chemosynthesis uses chemical reactions, the oxidation of molecules like methane and hydrogen sulfide, to power the same basic conversion. The energy source is different. The sunlight is replaced by chemistry, but the output is similar: organic matter, carbon fixed into biological molecules, the building blocks of living tissue. The organisms that perform chemosynthesis, bacteria and archaea, the ancient single-celled life that predates complex cells by billions of years, are the primary producers down here. They are the base of the food web. They are what everything else ultimately eats. The mussels ringing the brine pool are a beautiful example of how complex life has arranged itself around this chemical foundation. These are not ordinary filter-feeding mussels pulling plankton from the water column, because there is no plankton here, no sunlit surface with its blooms of microscopic plant life. Instead, they belong to a group sometimes called Bathymodiolus-type mussels, and they carry their food source inside themselves. Their gills are colonized by chemosynthetic bacteria, methane-oxidizing bacteria that take up the methane rising from the sediment and use it for energy, passing the benefit to the mussel in the form of organic compounds the mussel can use. The mussel has, over the course of evolution, struck an arrangement with the bacteria that it houses, shelter, and a position close to the chemical resource in exchange for a share of the energy the bacteria produce. The mussel farms its own food inside its own body. It grazes not on sunlit pastures but on the slow chemical gradient rising from the seafloor below. And the stability of that arrangement, the reliability of the methane and sulfide seeping from the sediment over very long timescales, has made the environment around these seeps one of extraordinary longevity for the animals that have adapted to it. The tube worms, for example, which you would also find at cold seeps associated with the chemistry that creates brine pools, animals that look like tall, narrow tubes of white material with a red, feathery plume waving at the top, belong to species like Lamellobrachia, and they grow with extraordinary slowness in an environment that is stable but not rich by surface ocean standards. And in that slowness, in the patient accumulation of carbon in a quiet place where almost nothing disturbs them, they live for a very long time. Some Lamellobrachia individuals have been estimated at more than 250 years of age, possibly more than 300, growing a millimeter or two per year in the cold, pressure-heavy dark, adding their length one slow increment at a time, in a seep community that existed before anyone now alive was born, that was old when the political boundaries of the world above were being drawn and redrawn, that has been filtering chemistry from the seafloor since before the oldest living trees in the temperate forests were saplings. 250 years in absolute darkness, in a place the sun has never touched, eating chemistry from a geological formation laid down before humans evolved. That is the world ringing the brine pool's lethal shore. Not alien, not impossible, but following the same patient logic as everything else. Find the energy, arrange yourself around it, take as much time as time allows. And what is that energy precisely in such a place? It is worth pausing here to understand the mechanism fully, because the mechanism is the thing, the one elegant piece of reasoning that explains not just the brine pool but the halocline in a cenote and the river running along the floor of the Black Sea and the shimmering glass-like boundary that divers film in the Yucatan and describe consistently as looking like the surface of water seen from below. All of those things are the same thing. They are the same rule expressing itself in different geographies. The rule is this: water with more dissolved salt in it is heavier than water with less, not by a dramatic margin that you could feel lifting a bucket, but by enough. Enough that when the two waters meet, the heavier one sinks beneath the lighter one and stays there. It does not mix freely the way warm and cool air eventually blur into one another on a still evening, because the density difference creates a boundary layer, a pycnocline, that resists turbulent mixing. The heavier water below and the lighter water above are both liquid, both seawater in a broad sense, and yet they behave at their interface almost like two different substances. The general term for any layer where density changes sharply with depth is a pycnocline. When the change in density is driven principally by a change in salinity, oceanographers call it a halocline. When it is driven by temperature, a thermocline. In practice, in the deep sea and in cenotes and in stratified basins, these layers often overlap and reinforce one another, salinity and temperature both conspiring to make one water mass denser than another. But the effect is the same in each case, a visible, navigable, physical boundary between two bodies of water that occupy the same basin but refuse to become one. Typical ocean seawater carries roughly 35 parts of dissolved salt for every 1,000 parts of water. 35 parts per 1,000. That is the global mean, the baseline against which everything else is measured. The water in a brine pool does not have 35 parts per 1,000. It has, depending on the pool, somewhere between 120 and 200 parts per 1,000, and sometimes more, 3 to 8 times the normal concentration. And so the brine pool, filling a depression in the seafloor, pressed down into the lowest point the terrain offers, sits beneath the surrounding ocean water the way a pool of mercury sits beneath water in a glass, denser by enough that the interface between them holds. That interface, that boundary, is visible. Submersible cameras have filmed it from both sides. From above, looking down through the ambient seawater, it appears as a reflective surface, shimmering and distorted, the way a puddle looks from a certain angle in the right light. From below, which is to say from inside the brine itself, when an ROV descends through the boundary, the surrounding water above takes on the character of a sky. A dark, pressured sky, but a sky nonetheless. And at the boundary itself there is a blurring, a refractive shimmer, where the light passing from one density of water into another bends just slightly, producing the visual quality you see when hot air rises from a summer road and the world above it wobbles. The pycnocline does not feel like glass when a submersible arm dips into it, but it behaves like glass in the sense that it has a surface. The arm creates a ripple. The ripple spreads outward from the point of disturbance as ripples do on any body of water, and then the surface settles and the brine pool is still again. So the brine pool is not a magic trick. It is not a violation of the rules of water. It is a precise and obedient expression of them. Now consider where all that salt comes from, because this is the part that reaches back further in time than almost any other physical feature of the modern seafloor. The salt in the brine pools of the Gulf of Mexico does not come from the sea. It comes from beneath the sea, from a formation called the Louann Salt, a thick layer of evaporite deposited approximately 170 to 200 million years ago during the Jurassic period, when what is now the Gulf of Mexico was not yet a proper ocean basin, but a shallow, semi-enclosed sea repeatedly exposed to evaporation in a hot, arid climate. The water evaporated and left its salt behind, And this happened again and again over millions of years until the accumulated salt reached thicknesses of several kilometers in places. Then the gulf opened further, deepened, filled with ocean water and sediment, and buried the salt under hundreds of meters of rock and mud. Buried salt does not remain buried passively. Salt is less dense than most sedimentary rock, and under the weight of the sediment piling on top of it over millions of years, it flows. Slowly, geologically, slowly, but it flows. It rises into the overlying sediment in columns and domes called salt domes, pushing the rock aside and warping the seafloor above into ridges and depressions. The basins that form between these salt-driven ridges are called mini-basins, and they are the low points, the topographic bowls, into which brine preferentially collects. When circulating water finds its way down to the buried Louann Salt and dissolves some of it, and that brine-enriched water migrates back upward along faults and fractures, it seeps out onto the seafloor, and following gravity, as water always does, fills the mini-basins and rests there. This is the provenance of the brine pool. It is, in a real sense, a liquid archive of geology that is 200 million years old, the dissolved remnant of an ancient, evaporating sea, expressing itself at the modern seafloor because salt never really goes away. It changes form, it moves, it seeps and flows and accumulates, but the inventory of salt that the Jurassic left beneath the Gulf is still there, still working, still bleeding upward through the seafloor, one slow pour at a time. And the brine that emerges from these seeps is not cold in the way that the deep water around it is cold. The surrounding deep sea in the Gulf of Mexico at 1,000 meters depth is dark and heavy and carries temperatures near 4 degrees Celsius, which is near the temperature of a household refrigerator. The brine pool, ringed by the same darkness and the same pressure, can be measurably warmer, several degrees warmer. The reason is that the brine carries heat with it from deeper sources as it migrates upward, conducted through rock that itself grows warmer with depth according to the geothermal gradient, the simple rule that the Earth's interior is hot and that heat conducts outward toward the surface, including through the seafloor. A pool that has been fed by this slowly upwelling, slightly warmer brine holds its heat in the same stable, stratified way it holds its salt. The density difference at the boundary prevents the pool from easily exchanging temperature with the overlying water. This is the sense in which the Jacuzzi of Despair earns the first part of its name. At roughly 1,000 meters depth in the Gulf of Mexico, where the team, including Erik of Temple University, studied it in 2016, the pool sits at the bottom of a depression, circular, approximately 30 meters in circumference and close to 4 meters deep at its deepest point, with a raised rim that gives it the quality of a tub. The water inside is warm relative to its surroundings. It is rich with dissolved methane and hydrogen sulfide rising from the seep below, and it is, at any meaningful biological concentration of oxygen, essentially devoid of it. The combination of extreme salinity, chemical toxicity, and oxygen absence means that most animals entering the pool do not leave it alive. The evidence of this surrounds the pool in the form of what researchers have described with a certain accurate bleakness as a bathtub ring. Around the margins, at the boundary where the brine surface meets the seafloor and the rim of the pool, and in the shallow regions where the brine is dense enough to be lethal, but perhaps not deep enough to fully submerge an animal, there accumulate the preserved remains of creatures that wandered in and could not get out. Crabs, amphipods, isopods, preserved not by any deliberate process, but by the same chemistry that makes the pool lethal. Anoxic, chemically hostile water is also water in which the ordinary agents of decomposition cannot operate. There are no bacteria performing aerobic breakdown. There are no scavengers willing to enter. The animals that die in the brine pool remain there, whole and recognizable, recorded in the sediment at the pool's edge, the way specimens are recorded in a jar of fixative, a passive, an inadvertent museum of the pool's long, lethal history. The rim itself, however, tells a different story. Because death and life are not the same thing, and the chemistry that kills an animal that has evolved to breathe oxygen is, for an animal that has evolved to metabolize sulfide or methane, simply food. The rim of the Jacuzzi of Despair, the elevated edge where the brine surface meets the seafloor and the chemical gradient is steepest, is crowded. Dense aggregations of mussels, their shells dark and tightly packed, colonize the margin. These are not ordinary mussels in any functional sense. Their tissues harbor chemosynthetic bacteria, symbionts living within the mussel cells, oxidizing methane and using the released energy to fix carbon to build the organic molecules that the mussel lives on. The mussel provides the bacteria with access to the chemical substrate they need. The bacteria provide the mussel with nutrition. Neither would thrive in this place without the other. And so we leave the rim of that lethal pool, one of the mussels packed tight along its elevated margin, their symbionts burning methane in the dark, and we carry the single rule with us into deeper, stranger water. Salt makes water heavy. Heavy water sinks, and wherever it sinks, it carries its character with it, its warmth, its chemistry, its solitude. That rule, stated so plainly that a child might nod and say yes, of course, is the key to something that even experienced oceanographers, when they first saw the data, had to stop and look at twice. Because it does not happen only in still pools. It happens in rivers. In the year 2010, a team of researchers from the University of Leeds sent an autonomous underwater vehicle into the Black Sea. Not to the surface of the Black Sea, where ships cross and birds turn in the wind and the water looks like any other water under any other sky. Down through the full water column, past the depth where light fades, past the depth where oxygen begins to disappear, all the way to the seafloor beneath the Bosphorus, the narrow strait of water that connects the Black Sea to the Sea of Marmara, and through Marmara to the Mediterranean beyond. What the vehicle found on that floor, and what the data it gathered showed when the team processed it afterward, was something that required a moment of quiet reorientation before it could be properly understood. There was a river down there, not the remains of a river, not a valley cut long ago when the seafloor was dry land, a river that was flowing, a river with water in it, moving water, water with a direction and a speed, and this is the part that takes a breath to absorb. Banks, levees, meanders. The vehicle mapped a defined channel, sculpted and maintained by its own current, the way the Mississippi maintains its channel or the Thames cuts and shapes the clay of its bed. The water in that channel was moving along the floor of the Black Sea the way a river moves along the floor of a valley, hugging the bottom, following the contours of the land. Except it was not land, it was the sea floor. And the water in the channel was not river water flowing under open sky, it was water flowing under more water. To understand how, you carry the rule forward from everything the earlier part of this night has already laid down. The Mediterranean Sea is saltier than the Black Sea. This is a long-established fact of the region's geography and hydrology. The Mediterranean is a nearly enclosed sea in a warm, dry climate, and it loses more water to evaporation than it receives from rain and rivers, which means the salts dissolved in it become gradually more concentrated, the way soup concentrates when you leave the lid off. The Black Sea, by contrast, receives enormous freshwater inflow from rivers like the Danube, the Dnieper, and the Dniester, great rivers draining much of Eastern Europe, and it sits in a cooler, wetter basin. It is less salty, measurably, significantly less salty. And when the surface level currents push Mediterranean water through the Bosphorus into the Black Sea, the two waters do not blend easily because they have different densities. The saltier Mediterranean water is heavier, and heavy water, as we have by now established in the calmest possible terms, sinks. It sinks and it keeps going. It cannot mix easily with the fresher, lighter water above it, because the difference in density resists that mixing the way oil resists mixing with water when you tilt the bottle. The physics does not care whether you are in a kitchen or at the bottom of the sea. Denser fluid settles beneath lighter fluid and stays there if the difference is large enough and the conditions allow. In the Bosphorus and the northern approaches to the Black Sea, the conditions allow. The dense Mediterranean water pours in and down, and once it is down, it does what all water does. It flows toward the lowest point. It follows the seafloor, it carves and sculpts and maintains a channel as it goes. The channel the University of Leeds team mapped was, by any measure, not a small thing. In places it reached roughly 35 meters in depth, deeper than the water in many small lakes. In width, it stretched up to about 1 kilometer across at its widest, which is broader than the Thames where it passes through central London. The flow rate the researchers estimated was in the range of 22,000 cubic meters per second. That number is worth holding still for a moment, because cubic meters per second is the unit in which large rivers are measured, and 22,000 of them per second is a great deal of water moving very quickly. The Amazon River, the largest river on Earth by discharge, carries something close to 209,000 cubic meters per second in its full flood, which is in another category entirely. But the Black Sea undersea river, at its estimated rate, would place among the 6 largest rivers on Earth by volume if it flowed across the surface instead of across the bottom of a sea. There is more water in that channel moving at that rate than in the Nile, than in the Mississippi, than in the great rivers whose names you learned in school and think of as definitionally large. It flows without banks in the ordinary terrestrial sense because on the seafloor there is no exposed soil, no reeds growing in the mud, no herons standing at the margin watching for fish. But there are levees, the same process that builds levees along surface rivers. Sediment deposited by the current at its edges, the material that falls out of the flow where the water slows, builds raised edges along this underwater channel too. The river deposits its load where its energy drops, and those deposits accumulate into walls, and the walls keep the current confined, and the current keeps cutting the channel deeper and narrower in a feedback that a geomorphologist studying the Mississippi would recognize completely. The form is the same because the physics is the same. The scale and the setting are different. The underlying rule is not. And there are, according to the data and the popular accounts that followed the 2010 paper, structures interpreted as analogous to rapids and waterfalls, places where the seafloor drops steeply enough and the flow accelerates enough that the current becomes turbulent in a way that mirrors the turbulence of water falling over a rock shelf in a mountain stream. These are analogies carefully applied. There is no spray. There is no sound that would travel to a surface where anyone stands and listens. There is no mist catching the light. There is only the dense, cold, salty water accelerating over a drop in the channel floor and tumbling in a way that instruments can detect and map, a ghost of the thing we call a rapid in the world of air and light, playing out in total darkness beneath 300 meters of water and the entire volume of the Black Sea. Which brings us to the Black Sea itself, because the Black Sea is not simply a backdrop for its undersea river. It is one of the most unusual bodies of water on Earth in its own right, and understanding the river means understanding the sea it flows into, and what makes that sea the particular kind of place it is. Below roughly 150 to 200 meters in the Black Sea, there is almost no oxygen. Below that depth, the water is what scientists call anoxic, from the Greek for without oxygen. And in the Black Sea specifically, the word used is sometimes euxinic, from Pontus Euxinus, the ancient name for this sea. Euxinic means not only devoid of oxygen but dominated by hydrogen sulfide, which forms when sulfate-reducing microbes in the sediment break down organic matter in the absence of oxygen and release hydrogen sulfide as a byproduct. Hydrogen sulfide is the compound that gives rotten eggs their smell, and in the Black Sea's deep water it is present in substantial concentrations, producing a cold, dark, sulfidic environment that most animals cannot survive in at all. The Black Sea is the world's largest body of anoxic water. That is a superlative that tends to land quietly when first heard, because the Black Sea is not a particularly obscure body of water. It has coastlines shared by Turkey, Romania, Bulgaria, Ukraine, Russia, and Georgia. Resorts and ports and ferry routes and fisheries have operated on its surface for thousands of years. But beneath a relatively shallow and well-mixed upper layer, the water below 200 meters is as lifeless and still and chemically alien as anything on this planet's surface. Sulphurous, dark, cold, and utterly without the oxygen that most of the life we know requires to function. What this means for the undersea river is ecologically significant. The dense, salty current flowing in from the Mediterranean along the seafloor carries water that still contains dissolved oxygen. The Mediterranean surface, where that water originated, was in contact with the atmosphere. As the river flows along the floor of the Black Sea's euxinic deep, it is delivering something that the local environment profoundly lacks: oxygen. And with oxygen, nutrients that have been stripped from the overlying water by the anoxic chemistry and that accumulate in the Mediterranean origin current. The undersea river is not merely a geological curiosity, it is a delivery mechanism carrying chemical life support into a vast dead zone, an artery threading through a place where otherwise the oxygen debt would be absolute and permanent. How exactly the organisms of the deep Black Sea interface with this input, at what scales and distances, is a matter of ongoing study. But the principle is established. The river matters biologically as well as physically. It is not separate from the living world beneath the Black Sea. It is, in one sense, its lifeline. And there is something else the anoxic Black Sea offers, something utterly unlike the lethal brine pool, but sharing its capacity for preservation. In the cold, sulfidic, oxygen-free deep water of the Black Sea, nothing can decompose in the ordinary way. The microbes that perform aerobic decomposition and the bacteria that would, in any ordinary seawater, break down wood and fiber and hull and rope into their constituent atoms within years or decades, cannot live in this water. They require oxygen, and oxygen is not there, which means that objects that sink into the Black Sea's deep zone are effectively removed from the process of decay. They do not rot. Archaeologists and marine historians have known this, at least in principle, for some time. And in recent decades, expeditions into the Black Sea's deep waters have confirmed it with a specificity that can be difficult to fully take in. Ancient wooden ships, vessels whose hulls were laid down when Rome was the center of the world, or earlier, or at times intermediate between those and the present, have been found on the floor of the Black Sea in states of preservation that no sunlit, oxygenated sea could produce. Their timbers are intact, their masts stand, the grain of the wood is visible. In some cases, artifacts are lying on the deck where they were last placed before the ship went down. The Black Sea has been keeping them, in the dark and the cold and the sulfide, as carefully as any museum could. On a surface that is alive and light and busy with ships, the deep is a library no one could have planned. A place where the same chemistry that makes it uninhabitable for most life makes it perfect, unintentionally, for the storage of the human past. Wood-boring organisms, the mollusks of the genus Teredo, shipworms, the bane of wooden-hulled vessels in every other sea, cannot live in anoxic, sulfidic water either. They need oxygen, they need organic material to digest and wood to bore into, but they also need to breathe, and in the Black Sea's deep they cannot. So the ships lie whole, not carved into lace by boring animals over centuries. not buried under sediment that shifted and disturbed them. Lying as they sank, held in the dark cold by the same chemistry that marks the deep Black Sea as one of the strangest places on the planet's surface. And carrying that strangeness back to the mechanism, to the rule we have been turning in our hands since the beginning of this night. The undersea river that flows into this space is itself one more expression of the same fundamental physics. Denser water sinks and flows beneath less dense water. In the Black Sea, the Mediterranean's saltier contribution becomes a river on the floor. In the brine pools of the Gulf of Mexico, the ancient salt of the Louann Formation bleeds upward through the rock and pools in the low places, a lake within a sea. In the halocline of a cenote, fresh rainwater floats in a distinct layer above the salt water that seeps in from the coast, and where the two meet, there is a shimmering optical boundary that divers pass through and describe, always reach for words for, as like passing through a membrane, like entering another liquid, like moving through something that is not quite air and not quite water, but the visible seam between two worlds. These are all one thing. The cenote and the brine pool and the Black Sea River and the shimmering membrane are different names for the same patient insistence of density. The insistence that denser fluid will find the bottom, will gather, will hold its boundary against the lighter fluid above it, and will persist there until something disrupts the system with enough energy to mix them. In the deep sea, that energy rarely comes. The bottom of the Black Sea has been stratified, anoxic, sulfidic, for thousands of years. The brine pools of the Gulf have been accumulating in their seafloor depressions for timescales that are hard to make vivid. The undersea river of the Bosphorus has been flowing, not exactly continuously in its current form, because sea levels have changed, and the Bosphorus connection has not always been what it is today, but the principle has persisted. As long as the salinity difference between the Mediterranean and the Black Sea has persisted. This is what physicists mean when they speak of stable stratification. The system resists mixing. It is not unstable and liable to flip without much provocation, the way a pencil balanced on its tip is unstable. It is stable the way a book lying flat on a table is stable. It requires a deliberate intervention, a significant input of energy to disturb it. And without that intervention, it simply continues, quietly, and without any particular drama, being what it is. A lake on the floor of the sea, a river beneath the water, a shimmer in the dark where one layer meets another. The gravity current, the term scientists use for what the Black Sea's undersea river is, or what any of these density-driven bottom flows are, is a phenomenon that operates at many scales and in many contexts. It is not unique to the exotic deep sea, though the deep sea produces the most dramatic examples. When cold, dense Arctic air drains down a mountainside on a still night and pools in the valley as a frost hollow, that is a gravity current. Dense fluid flowing downhill beneath lighter fluid, exactly the same principle, playing out in air instead of water. When sediment-laden river water, heavy with suspended mud, flows out over the continental shelf and plunges down the slope beneath clearer, lighter seawater, that is a turbidity current, another variant of the same gravity-driven flow. When the salty outflow from the Mediterranean pours through the Strait of Gibraltar and sinks beneath the less salty Atlantic water, spreading westward along a density horizon hundreds of meters down, that is the same physics expressed on an oceanic scale. The Bosphorus just gives us the most vivid version and the most clearly river-like version because the geometry of the strait concentrates and directs the flow into something compact enough for an autonomous vehicle to map, compact enough to have banks and a defined channel, and a measurable width and depth. But the rule is everywhere that density differs, everywhere that one fluid is heavier than another and has a path to the low ground. And in the Black Sea, below the undersea river, below the anoxic deep, below the preserved ships and the sulfide chemistry that keeps them whole, the floor continues, and the sediments continue to accumulate, and the layers build and compress, and the organic material in them, the dead organic matter of thousands of years of productivity in the well-lit surface layer above, raining slowly down through the oxygen-depleted column, undergoes the slow transformations that produce, given time and pressure and the work of microbes, the same compounds that make the brine pools dangerous and the seep ecosystems possible, methane, and the possibility of what happens when methane rises. But that opening leads us forward into the next chamber of this night's long descent, toward the cold seeps and the creatures that cluster at them, and the chemistry that holds entire ecosystems together without a single photon of sunlight. We will come to them gently. There is no rush. The waters here are slow and cold and dark and entirely patient, and we can afford to be patient too, moving through them the way the brine moves, steadily, without urgency, following the contour of the low places, going wherever the weight of things leads. The autonomous vehicle that mapped the Black Sea's undersea river was following in its way the same logic. It was sent down because someone wanted to know what was there, what was actually there, below the surface of a sea that people have navigated and lived beside for millennia, in the part of it that no one walks beside and no ship's keel grazes. And what it found was a river. A thing so familiar in name and concept that children draw it in crayon. The blue line on the page, the banks on either side, the directional arrow showing where it goes, made alien by its location, made impossible seeming by the fact of what it is surrounded by, and made completely comprehensible, ultimately, by the same physics that governs everything else that moves on this planet. Heavy things fall, dense things sink, and wherever there is a difference in density, there is the potential for movement, for flow, for the slow, gravitational sorting of the world into its layers. The Black Sea expresses this as a river on its floor. The Gulf of Mexico expresses it as a pool with its own shoreline and its own tides of a kind, its own surface that an ROV can ripple. The cenotes of the Yucatan express it as a shimmering, invisible boundary that divers fall through in a blurring of light, entering a saltier world with a step that leaves no ripple except in the optical layer between. All of these things are real, all of them have coordinates, all of them were measured by instruments and studied by people with funding and proposals and years of work invested in understanding them. The University of Leeds sent a vehicle. Erik and his colleagues at Temple University sent an ROV into the Gulf. Divers with tanks and lights have passed through the haloclines of cenotes and filmed what they saw. These are documented facts in a world that is, if anything, more strange and more structurally bizarre than the folklore ever managed to make it. The sixth largest river in the world by flow has no name on any map that most people have ever consulted. It moves in the dark 200 or 300 meters beneath the surface of the Black Sea, between banks that no one will ever stand on, toward a deep zone where the water is toxic to almost everything that breathes. It carries the chemistry of the Mediterranean into the chemistry of the Black Sea, and it has been doing so in some form for as long as those two seas have been connected by the narrow channel of the Bosphorus. It feeds the dead zone with something the dead zone lacks. It maintains a channel by its own erosive energy. And it does all of this without any light, without any atmosphere, without any of the context that makes a river recognizable as a river to the minds that evolved alongside rivers and have always lived near them. It is a river the same way an underground cave river is a river, real in its physics, real in its flow, real in the way it shapes the rock it moves through, but stripped of everything that makes a river feel like a river to someone standing on its bank at dusk, watching the current, feeling the breeze off the water. There is no breeze here, there is no dusk, there is pressure, immense and steady, there is cold. There is the faint chemical signature of Mediterranean salinity tracing its way through the dark, following the contour of the seafloor the way all water follows the contour of whatever is beneath it, patient and unhurried and utterly obedient to the rule. Salt makes water heavy. Heavy water sinks, and where it sinks, it flows, and where it flows, it carries. This is not magic. It was never magic. It is something older than magic, a physical principle so fundamental and so universal that it operates at every scale, from the kitchen counter to the floor of a sea that has no name for its own bottom. And the fact that we can now send instruments down to that bottom and map what is there, and come back with data that resolves into a picture of a river with banks and rapids and a flow rate we can compare to the Nile. This is not a diminishment of the wonder. It is the wonder made exact. It is the wonder made real in the particular way that real things, named and measured and located, are real. The deep waters of the Black Sea hold the river on their floor and the ships of the ancient world in their stillness and the sulfide chemistry that makes them both possible. And above all of this, the surface of the sea goes on being a sea, blue and grey and wind-roughened and full of the ordinary life of the upper water column, the sunlit zone where plankton bloom and fish school and fishermen have worked for thousands of years without any reason to think about what lay below the reach of light and oxygen. We are thinking about it now. It is a good thing to think about before sleep, not because it is unsettling, but because it is clarifying, because it is a reminder that the world has depth, literal depth, that we have barely begun to describe, and that what hides in those depths follows rules we know, rules that operate everywhere, rules that have been working without our attention since long before there was anyone to pay attention. The river in the Black Sea does not need us to know about it. It does not need the University of Leeds or the autonomous vehicle or the paper that was published in 2010. It would flow without any of that. It has flowed without any of that for a very long time. But we know about it now. And knowing about it, holding the picture of it in the mind, the dark channel and the levied banks and the slow, salty current flowing toward the anoxic deep, is in its way a form of company. A reminder that the world is enormously larger than the room you are lying in, and that this largeness is not threatening but simply true, simply the scale of things, and that within that scale everything follows a pattern, a rule, a physical logic that does not require belief or interpretation and does not change depending on who is watching. The river flows. The heavy water finds the low place. The brine pools gather in their Gulf of Mexico depressions, fringed with mussels and ringed with the preserved remains of things that wandered too close. And somewhere far from here, in the dark beneath a sea that connects the Mediterranean to the ancient world's eastern edge, water is moving along a channel, carrying its chemistry, following the contour of the floor, doing what heavy water does. We go now toward the life at the edge of all of this, the life that has found a way not just to endure the lethality of these chemical worlds, but to eat it, to make a living from it, to build communities so specific and so improbable that their discovery changed the way biologists think about where life is possible and how energy can flow through an ecosystem. And there is life here. It is not life despite the chemistry, it is life because of it. This is the thing that takes the longest to settle into understanding, and it is worth taking slowly because it is genuinely one of the more remarkable shifts in biological thinking that the 20th century produced. For most of human history, for essentially all of it in fact, the assumption was so deep it barely registered as an assumption at all. Life runs on sunlight. Plants capture it, animals eat the plants, other animals eat those animals, and the whole elaborate architecture of a food web in a forest or a prairie or a coral reef is ultimately a structure built on photons falling from the sky. Take the sky away, and the energy is gone and the life collapses. Until 1984, this felt so obvious as to be barely worth stating. In 1984, in the Gulf of Mexico, researchers encountered their first cold seep, and the picture changed. A cold seep is not a hydrothermal vent. That distinction matters, and it is worth holding clearly because the two are sometimes confused in popular accounts, and confusing them is a little like confusing a quiet spring in a meadow with a geyser. Both involve water moving through rock and arriving at the surface, but they are entirely different machines. A hydrothermal vent is hot. The water emerging from it has been superheated by proximity to volcanic activity beneath the seafloor, and it can emerge at temperatures of 300 degrees Celsius or more, kept liquid only by the immense pressure of the deep ocean above it. The chemistry around a hydrothermal vent is driven partly by that heat, and the communities that live there are adapted to an environment that feels, from a distance, like something from a furnace. A cold seep is not hot. The fluid seeping from it is close to the ambient temperature of the deep seafloor. Cold, dark, pressurized, and still. What makes it remarkable is not heat, but chemistry. The fluid is rich in methane, rich in hydrogen sulfide, and in the deep ocean where sunlight never reaches and the organic rain from the surface is sparse and slow, methane and hydrogen sulfide are forms of energy. They are fuel, not the kind of fuel an engine burns, but fuel in the biochemical sense, a molecule whose chemical bonds contain potential and whose oxidation releases energy that can be captured and used to build organic matter. This is chemosynthesis, and it is to these seeps what photosynthesis is to a sunlit meadow above the sea. The same fundamental transaction, chemical energy captured and turned into life, but powered not by light and carbon dioxide, as in a leaf, but by methane and sulfur compounds in the dark at the bottom of the ocean. The organisms doing this most directly are bacteria and archaea. Microbes, in other words, single-celled, ancient, invisible, and extraordinarily capable. They coat the seafloor around the seeps in mats, thick, sometimes colorful mats, of white or orange or yellow, marking the places where the chemistry transitions and the energy is richest. These mats are visible in submersible footage as bright patches in an otherwise featureless mudscape, and they are, in a sense, the meadows of this sunless world. The primary producers, the base of the food web, the organisms that turn raw chemistry into living tissue. But they do not do it alone, and the way they do it is strange enough to deserve its own moment of attention. Among the most conspicuous animals at cold seeps are the mussels. Not the mussels you might eat at a restaurant on a warm evening somewhere above the sea, though they are genuinely related to those, but a group often referred to as Bathymodiolus-type mussels, deep-sea mussels whose gills are packed, impossibly densely, with chemosynthetic bacteria. The bacteria live inside the mussel. The mussel provides the bacteria with a platform and access to both methane and oxygen, drawing seawater across its gills. The bacteria oxidize the methane, capture the energy, and produce organic compounds. The mussel, in turn, eats those organic compounds. The mussel is, in effect, a living chemical reactor. It does not need to filter plankton from the water the way a coastal mussel does. It does not need sunlight, even indirectly. It carries its food source inside its own body, farming the chemistry of the seep in every breath it takes. And because the seep keeps leaking and the chemistry keeps flowing, the mussels can build up into dense beds, hundreds, thousands, draping the rim of a brine pool or clustering across a carbonate pavement in numbers that look, from a submersible window, almost like a tidal flat transplanted to a place that has never seen a tide. Those mussel beds around the Jacuzzi of Despair, the ones mentioned in the 2016 study led by Erik at Temple University, they are there for exactly this reason. The brine pool leaks methane and hydrogen sulfide. The mussels harvest it through their bacterial symbionts. The pool is lethal to animals that swim into it, but the margin, the edge, the chemical gradient between the lethality inside and the ordinary ocean outside, that margin is extraordinarily rich. A halo of life encircling a zone of death, a shoreline in more than one sense. And the mussels are not alone at the rim. There are tube worms. The tube worm deserves a moment simply because it is one of those creatures that, once you know about it, becomes hard to forget. It lives inside a tube of its own secreting, a long, thin, flexible cylinder of chitin anchored to the seafloor or to a carbonate surface. And it does not have a mouth. No mouth, no gut, no digestive system at all in the adult form. What it has, where a gut would normally be, is a dense mass of tissue called a trophosome, packed so thickly with sulfur-oxidizing chemosynthetic bacteria that the organ is essentially a bag of microbes, red from the hemoglobin the worm uses to carry both oxygen and hydrogen sulfide to the bacteria simultaneously. The worm breathes for its passengers. The passengers feed the worm. The arrangement is so thorough that the worm has given up the capacity to feed in any other way. The species most associated with cold seeps, Lamellobrachia, and its relatives, grows slowly. Very slowly. The stable, cold, chemically consistent environment of a deep seep does not demand urgency. There is no season, there is no storm season, no winter, no drought. The seep flows, the bacteria metabolize, the tube worm grows a fraction of a millimeter at a time, year after year. Some individual Lamellobrachia tube worms are estimated to be 250 years old. Some may exceed 300 years. They were alive in the dark at the bottom of the Gulf of Mexico before the United States existed as a country, before the Declaration of Independence was signed, before most of the landmarks you think of as old were built. They were growing slowly in their tubes while the world above them changed beyond recognition, and they did not notice. And they continue now, tonight, extending slowly downward into the sediment. 300 years in the dark, eating the chemistry of a seep. Inside a tube, you secreted yourself. This is what cold seeps make possible. Now, among the organisms doing the deepest chemical work at these seeps, organisms that are not mussels or tube worms, but something far more ancient, far smaller, and arguably far more important. There is a consortium that has only been understood in the last few decades, and which turns out to be doing something globally significant. The process is called the anaerobic oxidation of methane, AOM in shorthand. And the way it works is this: archaea, a domain of single-celled microorganisms that are not quite bacteria, though they look similar, representing one of the most ancient lineages of life on Earth, attach themselves in close physical contact with sulfate-reducing bacteria. Together they carry out a chemical reaction that neither of them could complete alone. The archaea reverse the usual chemistry of methane production, oxidizing methane instead of producing it, passing the electrons somewhere. The sulfate-reducing bacteria accept those electrons and reduce sulfate to sulfide in the process. The two organisms are metabolically coupled, a partnership so tight that some researchers have described them as a single metabolic unit living in two bodies. The product of all this, from the perspective of the seafloor ecosystem, is hydrogen sulfide, which feeds the other chemosynthetic communities above, and energy, which the consortium shares between itself. But the substrate, the thing being consumed, is methane. And this matters enormously at a scale that extends far beyond the seep itself. Methane is a greenhouse gas, a potent one. The seafloor sits above enormous quantities of it. Methane produced by microbial decomposition of organic matter in deep sediments, methane that has been migrating slowly upward through the rock for millions of years, methane associated with oil and gas deposits and with the methane hydrates we will come to in a moment. If all of it reached the atmosphere, the implications for the planet's climate would be severe. But most of it does not reach the atmosphere because the AOM consortium is sitting at the sediment-water interface at the cold seeps in the anaerobic zones just beneath the seafloor, consuming methane before it escapes. It is estimated that the anaerobic oxidation of methane consumes somewhere between 70 and 90% of the methane rising from marine sediments globally. Not a trace amount, not a rounding error, the overwhelming majority. The seafloor eats its own methane before it can become our problem, and the organisms doing the eating are archaea and bacteria, invisible and ancient, conducting chemistry in the dark, completely indifferent to the fact that what they are doing has kept the atmosphere more stable than it would otherwise be. They have been doing this for a very long time. We learned about it very recently. These are not the same thing. Now, one byproduct of the anaerobic oxidation of methane is carbonate. When the chemistry runs, dissolved carbonate is produced as a secondary output, and that carbonate does not stay dissolved. In the cold, pressurized, mineral-saturated environment of the deep seep, it precipitates. It crystallizes. It falls out of solution and accumulates on the seafloor as solid rock. This is orthogenic carbonate, carbonate that forms in place on the seafloor from the chemistry of the seep itself. And over time, long time, seep time, the slow accumulation of a stable environment that lasts for thousands of years, the carbonate builds up into structures, pavements and slabs and mounds and chimney-like formations rising from the seafloor, hard and pale and sculptural, a reef built not by corals but by chemistry, by the slow precipitation of the methane-eating archaea's metabolic byproduct. These are the methane mounds, and they can be substantial, not towering, not dramatic in the way a hydrothermal vent chimney might be, but real, solid, measurable elevations on the seafloor shaped by biology acting on geology across centuries and millennia, as patient and as certain as any geological process above the sea. Methane mounds are also often associated with something that sits in a category entirely of its own: methane hydrate. If you have not encountered methane hydrate before, the concept takes a moment to settle because it sounds contradictory. Methane is a gas. Water is a liquid. Ice is a solid. How then can you have methane ice? The answer is pressure. And the architecture of water molecules. At very high pressures and very low temperatures, the conditions that prevail in deep seafloor sediments, typically below about 300 to 500 meters of water depth, though the exact window depends on local temperature. Water molecules arrange themselves into crystalline lattice structures, cages. Each cage is a small cluster of water molecules held together by hydrogen bonds, forming a hollow geometric form. And into each of those cages, if the chemistry is right, a molecule of methane slots itself and is held there, surrounded by ice, locked in place not by covalent chemical bonding, but simply by the geometry of the structure. Methane inside a cage of water. Methane clathrate. Methane hydrate. On the seafloor, where these conditions are met, methane hydrate looks like dirty ice. Pale yellowish white, slightly translucent, coated with sediment. ROV cameras have filmed it resting on the seabed, sometimes in chunks or nodules, sometimes in exposed layers where the seafloor has been disturbed or where the hydrate has formed at the surface of the sediment. It is cold, it is solid, and it is full of methane. If you bring a piece of it toward the surface, decreasing the pressure, warming it slightly, it dissociates, the cages destabilize, the methane escapes in a fizzing, bubbling rush, and if you hold a flame near it as it does this, the escaping methane ignites, ice that burns. The phrase sounds like something from a story, but it is simply a description of the chemistry, a solid made of water, containing a flammable gas which releases and ignites when the pressure and temperature conditions change. The global extent of methane hydrate in marine sediments is very large. The total methane locked in seafloor hydrates is estimated to be substantial, and the concern among climate scientists is not trivial. If the deep ocean warms enough, if the temperature and pressure window that keeps the hydrate stable shifts upward through the sediment column, the hydrates could dissociate and release their methane into the water column, and eventually the atmosphere. This is one of the feedback mechanisms that figures in discussions of long-term climate risk. Not imminent, not simple, not a switch that flips overnight, but a process worth understanding, and one that the organisms of the cold seep, in their chemosynthetic work, are in some sense guarding against consuming methane in the water before it can reach the surface. The seep community, the mussels and the tube worms and the bacterial mats and the archaea in their anaerobic quiet, is not only a biological marvel, it is a planetary function. It is the seafloor doing one of its jobs, slowly, in the dark, without ceremony or acknowledgement. Now the world has more of these places than many people realize. The Gulf of Mexico, where the Jacuzzi of Despair sits and where the first cold seep communities were documented in 1984, is in many ways the best studied of these environments. But brine pools and cold seeps and the strange layered chemistry that produces them occur across the ocean basins, wherever the geology cooperates, wherever ancient evaporites are buried deep enough and the pressure gradients are right, wherever the sediments contain enough organic material to fuel the microbial machinery. The Red Sea has them. The Red Sea's brine pools are different in character from those in the Gulf of Mexico because the Red Sea's geology is different. The Red Sea is a young ocean in geological terms, a spreading rift that has been pulling Arabia away from Africa for roughly 30 million years. The floor of the rift has ancient evaporite layers buried deep, and in several places along the axial valley, the brine that dissolves from these layers has collected in deeps that are not only hypersaline, but hot, hydrothermally hot. The Atlantis, too. Deep is the most studied of these. It sits at roughly 2,000 meters of depth in the central Red Sea, and the brine that has pooled there is not merely salty but warm, around 60 degrees Celsius at the deepest layer, and metal-rich in a way that makes geologists and mining engineers and policy researchers take notice. The brine of the Atlantis, the Ku. Deep contains dissolved iron, zinc, copper, silver and gold, not in commercial quantities at the surface, but present in the water and accumulating as metalliferous sediments on the pool floor. A pool of hot, salty, metal-laden water sitting at the bottom of the Red Sea, preserving a record of hydrothermal chemistry as the rift continues to widen. The communities around the Atlantis, too, deep are different from those around the Gulf brine pools because the environment is different, hotter, geochemically distinct, the boundaries drawn by temperature as well as salinity. But the basic architecture is recognizable, a layered chemistry producing a lethality in the pool and a richness at its margins. Then there are the Eastern Mediterranean, deep, hypersaline, anoxic basins. The Eastern Mediterranean is geologically complex, and beneath the seafloor, in the deep sedimentary sequences of basins like the Levantine and Ionian, there are ancient evaporites. Salt deposited when the Mediterranean was shallower, warmer, and periodically nearly dry during the Messinian salinity crisis about 5 to 6 million years ago. Brine dissolving from these evaporites has collected in a series of deep, enclosed basins in the eastern Mediterranean floor, and several of these basins are among the most extreme aquatic environments on Earth. L'Atalante Basin, Discovery Basin, Urania Basin. These are the names given to bodies of water that sit at depths of around 3 to 4 kilometers below the Mediterranean surface, and they are so salty and so devoid of oxygen that the water in them is essentially a saturated brine, anoxic from top to bottom, separated from the normal Mediterranean above by a halocline of extraordinary sharpness. Fish cannot survive in these basins. The salinity alone would extract water from their cells through osmosis, and the absence of oxygen would kill them before the salt had a chance to do its work. For a long time, it was assumed that essentially nothing could live in the basins themselves, at the bottom, in the brine, in permanent anoxia, with no oxygen and salt concentrations multiple times that of seawater. And then researchers found loriciferans. Loricifera is a phylum, a major branch of the animal kingdom, comprising tiny meiofaunal organisms that live between the grains of marine sediment. They were only described as a group in 1983 within living memory, which is a reminder of how recently we have come to understand the taxonomy of the deep sea floor. They are animals, multicellular, with bodies and nervous systems and reproductive strategies, everything that distinguishes animal life from microbial life. And in the sediments of the Eastern Mediterranean, deep hypersaline anoxic basins, specimens were found that appeared to be living their entire lives without oxygen, not surviving a brief excursion into anoxia, not tolerating it temporarily, living in it, reproducing in it, completing their life cycles in a medium that every textbook said was incompatible with animal life. The finding was controversial, as findings of this magnitude tend to be, but the evidence accumulated and the interpretation stands. Certain loriciferans appear to be the first multicellular animals documented to spend their complete life cycles in permanently anoxic conditions. They do not rely on oxygen-based metabolism in the way that almost every other animal does. They use different biochemical pathways, drawing energy from the chemistry of the anoxic brine itself. The category of where animal life is possible quietly expanded, not dramatically. The loriciferans are small and specialized and do not suggest that mammals will soon evolve to breathe sulfide. But the boundary moved, and boundaries that move are worth knowing about. Then there is the most recently discovered of the pools we are going to visit tonight. In 2022, a team led by researchers from the University of Miami, using a remotely operated vehicle, discovered a brine pool in the Gulf of Aqaba. The Gulf of Aqaba is the northeastern arm of the Red Sea, narrow and deep, separated from the rest of the sea by topography and reaching depths of nearly 2,000 meters. The pool they found sits at approximately 1,770 meters. It is small, relatively speaking, a pocket of hypersaline, anoxic brine collected in a depression in the seafloor of this young tectonically active arm of the Red Sea. The behavior of the pool was familiar: fish and shrimp that wandered across the sharp halocline at its surface. The transition from ordinary seawater to the dense, saturated brine were incapacitated and died. The researchers observed this directly with the ROV, watching animals essentially stun themselves on the brine's surface chemistry and become unable to escape, floating or sinking into the pool, preserved in its toxic chemistry. But the margins were alive, as they have been in every brine pool scientists have examined closely. The edge is where the chemistry is not lethal but merely intense, where the gradients between the brine's richness and the open water's oxygenation are steepest and most productive, where chemosynthetic microbes and their associated animals find the conditions they need. The rim of lethality is also a rim of life, every time. And then, finally, let us go somewhere warmer. Or at least somewhere that feels more familiar. Shafts of sunlight, a lagoon, the turquoise water of the Yucatan Peninsula in Mexico, where the limestone plateau that underlies the whole region is riddled with sinkholes. Cenotes, they are called in Spanish from the Mayan word for sacred well, and the Maya regarded them exactly as such, as openings into the underworld, places where the earth gave way and the water beneath was visible and touchable. They used them for fresh water, for ceremony, for offering. They are still visited in their thousands by people who come to swim and dive in their crystalline water. And in many of the deeper cenotes, something waits for the diver that has nothing to do with ceremony and everything to do with the same physics we have been following throughout this whole journey through the dark. The Yucatan Peninsula is porous limestone. Rain falls, percolates, dissolves the rock over centuries, creating cave systems and underground rivers. And in the coastal areas, where the fresh groundwater meets the intrusion of salt water from the sea, meeting it not at the coast but far inland through the connected rock, something builds up in the water column, a halocline. Fresh water sits on top, salt water sits below. The two do not mix because their densities are different. The fresh water, lighter, stays up. The salt water, heavier, stays down. And at the boundary between them, a layer forms that is neither one nor the other, but the transition between, and this transition layer bends light differently from either fluid. It separates because the refractive index of water depends on its salinity, and the gradient here is sharp. A diver descending into a cenote reaches this layer, this halocline, and the view ahead blurs. Not like dirty water or disturbed sediment. Like looking through a pane of glass that has been heated unevenly and warped, or like the shimmer above hot pavement on a summer road. The water ripples without moving. The rock on the other side seems to undulate gently. Other divers below the halocline look slightly distorted, their outlines wavering as if they are in a different medium, which in a meaningful sense they are. Some divers pause at the halocline and move their hands through it. The layer is not a solid surface. The hand passes through, but it passes through into a different density, and the transition is visible, tangible, in a sensory way that goes beyond what you might expect from a difference in dissolved salt. The diver is at a boundary inside water, a boundary between water and water, between two layers of the same substance that happen to behave in this particular way as though they are different things entirely. This is the halocline that divers describe as one of the more otherworldly experiences available in the accessible world. Not the deep ocean, not a specialized submersible, but a flooded cave in the Yucatan where a person can descend with fins and a tank of air and pass through a layer that looks like the surface of a pond from below. And it is the same rule. Fresh water and salt water have different densities. The denser fluid sinks, the lighter fluid floats, the boundary between them shimmers because light bends at the density gradient. There is no magic, there is only weight. There is only the same physical logic that pools brine at the bottom of the Gulf of Mexico and flows a salty current along the floor of the Black Sea and freezes methane into cages of ice at the pressure and temperature of the deep seafloor. The same rule everywhere: density. The tendency of heavier things to find the lowest place and rest there. This is the thought worth sitting with as we come now toward the end of this long, slow journey through the dark water. Everything we have seen tonight, the brine pool with its shoreline, the warm, lethal pool in the Gulf with its rim of mussels, the undersea river with its levied banks and its inferred rapids, the halocline that shimmers like the surface of a pond, the loriciferans in their anoxic brine, the tube worms growing in the dark for 3 centuries, the methane ice resting on the seafloor like a pale mineral ghost of something that should be a gas. Every one of these things is not a violation of the way water works. It is an application of the way water works. A precise, patient, completely consistent application. Water follows its own weight. Salt makes water heavier. Heavier water sinks beneath lighter water and stays there because the density difference resists mixing the way a stone wall resists a breeze. Not absolutely and not forever, but in the practical time scale of an ocean, effectively and completely. The sharp boundary between dense brine and ordinary seawater looks like a surface because it behaves like a surface. The heavier fluid will not easily rise and the lighter fluid will not easily fall. And the optical difference at the boundary, the shimmer, the distortion, is just light responding to the change in refractive index, the way light always does when it passes between media of different density. The Black Sea's undersea river is a density current. Cold, salty Mediterranean water is denser than the fresher water of the Black Sea above it, so it sinks, and once it has sunk, it flows downhill along the contour of the seafloor, following the gradient, building a channel through the sculpting action of the flow over time, creating levees from the sediment it deposits at its edges, moving as any river moves. Not because it was commanded to move, but because it is heavier than what surrounds it, and the floor slopes and gravity is constant. The cenote halocline shimmers because fresh water and salt water have different densities and different refractive indices, and at the boundary between them, light bends, and what we see through that bending is the ordinary physical reality of two layers in contact. The methane mounds are built by chemistry, the same chemistry that consumes most of the methane rising from the seafloor before it reaches the atmosphere, leaving behind as a kind of mineral signature the carbonate that precipitates from the reaction. The methane hydrate is solid methane in ice cages because that is what high pressure and low temperature do to the arrangement of water molecules around a small gas molecule. None of it is inexplicable. None of it requires the suspension of the rules. Every single feature we have looked at tonight is the rules working precisely and thoroughly in a place where most people have never thought to look for them. And this thought specifically, is what I find most worth carrying into sleep. The world is not a place where strange things happen at random. The world is a place where the rules run everywhere, even in the dark, even at depth, even in conditions so extreme they seem at first like exceptions. There is a lake at the bottom of the sea because heavy water pools. There is a river flowing beneath the Black Sea because dense water flows downhill. There is life ringing those lethal pools because wherever there is a chemical gradient, wherever there is energy available in any form, life has had 4 billion years to find a way to extract it, and it has not wasted the opportunity. The tube worms in their long, slow centuries, the mussels farming bacteria in their gills, the archaea conducting their quiet chemistry, and in doing so moderating the methane that might otherwise warm a planet they do not know exists. The loriciferans making their unhurried lives in brine that would kill almost everything we can name. All of it following the rules, all of it in a deep sense, intelligible. Not fully known. The ocean remains mostly unmapped, mostly unsampled, a volume of the planet so large that we have only begun, in the last few decades, to understand what kinds of things happen in it. But intelligible, knowable, following a logic that a person can hold in their mind and carry with them. The ocean floor is dark right now. It is always dark there. The brine pools sit in their Gulf of Mexico depressions without the need for our awareness of them. The Atlantis, too. Deep holds its hot, metal-rich water at 60 degrees in the Rift Valley of the Red Sea, accumulating its metalliferous sediments as the plates continue to spread, as they have been spreading for 30 million years and will continue to do for tens of millions more. The L'Atalante Basin, the Discovery Basin, the Urania Basin, their brine is still their loriciferans going about the unhurried business of their anoxic lives. The Black Sea River moves along its channel in the dark. The Lamellibrachia tube worms extend their plumes into the water column and breathe hydrogen sulfide to their bacterial passengers and grow a fraction of a millimeter and continue. None of it requires our witnessing to proceed, but it is real, documented, named, measured, photographed through the cameras of remotely operated vehicles that have been lowered on cables from ships by researchers who spent years getting there. Erik and his team in 2016, describing the Jacuzzi of Despair in terms precise enough that you can picture it. 30 meters in circumference, 3.7 meters deep at its deepest, the raised rim, the warm brine inside, the mussels draping the edge, the preserved carcasses in the interior. The University of Leeds team in 2010 sending an autonomous underwater vehicle along the floor of the Black Sea to map a channel that no instrument had ever traveled before. The University of Miami team in 2022 descending to 1,770 meters in the Gulf of Aqaba and finding another pool, another rim of life, another halocline, sharp as a knife between the ordinary ocean and the extraordinary brine. People went to look. And what they found was this: the world is more than we thought, and the rules that govern it are consistent enough that even the most improbable seeming features, a lake with a shoreline inside the ocean, a river with banks flowing beneath the sea, turn out to be expressions of the same humble, reliable principle that oil sits on water and cold air settles into valleys on still nights, and heavy things find the lowest place and rest. Denser fluid sinks. The rest follows. If you are still with me now, still listening to this, in whatever arrangement you have made for yourself in the dark, lying down perhaps, the weight of the blanket settled in the way blankets settle when you stop moving, the room cooling slightly as rooms do at this hour, I would like to ask you something before we part. Tell me if you feel moved too, where in the world you are listening from tonight. Somewhere with a night sky, somewhere with a different sea nearby, somewhere with mountains or desert, or the hum of a city that does not quite stop. I would genuinely like to know. The comments are there, and I read them. There are more of these slow journeys here, waiting. More dark water to descend into. More physics made strange by depth and pressure and time. More life found in the places where life should not, by any simple accounting, be. They will be here whenever you want them, but for now. The deep water is quiet. The brine pools sit undisturbed, their surfaces still as glass under a kilometre of ocean. The tube worms sway in the imperceptible current of the seep. The methane ice rests on the sediment in the cold, and the pressure and the dark, doing nothing, being exactly what it is. The Black Sea River moves slowly along its ancient channel, carrying its chemistry toward the anoxic deep, as it has been doing since long before anyone thought to measure it. You have followed a long way down tonight, further than most people go. Put down whatever is left of the day, set it down like something you have been carrying longer than you needed to, and simply let it rest. Like the old Stoics, let the day go. Tomorrow can be tomorrow's. Good night, sleep well.